we are going to work with picture language. All the needed functions are in runes.py. Runes will also import from graphics.py and image to gif.py. A quick note on importing modules. So for us to work with the picture language, we will have to import runes.py. So we say from runes import star. This star means all the functions inside runes.py will be imported. There are other ways to import modules. We can say import x. In this case, when we need to use a particular function inside x, we have to say x.name. We can also say from x import star, like what we did from the runes.py. In doing so, when we need a particular function inside x, we can say simply that something instead of x.something. We can also import specific function from a module x like this from x import a, b, c. So a, b, c are functions inside x that we imported, and we can use them as if they are already in our program as a, b, and c. We now want to play with the picture language. As before, there are three elements of programming: the primitives in this picture language, the ways that we can combine these primitives, and the ways that we can do abstraction. In the last video, we saw sequence and conditioner. In this video, we're going to see the third and important feature, that is looping. Let's start with the primitives that we can work with to create beautiful pictures. The operation available to us, first one, clear all. This is to clear up the screen so that it becomes empty again. Show a particular picture, and this picture is one of those that given to us as we will see it in the following. Quarter turn right picture. Given a picture, you can make a quarter turn, that means 90-degree turn to the right. Stack picture 1 on top of picture 2. Right, here are the pictures that we can work with: R cross BB, Nova BB, Sail BB, Corner BB, and Heart BB. What are these? Show a picture is to show this picture given to us. R cross BB is this. Show Nova BB, this is Nova. Show Sail BB, this is Sail. Show Corner BB, this is Corner. Show Heart BB, this is the Heart. Now, if we have show quarter turn right R cross BB, this is R cross. After quarter turn, you have this, right? 90-degree turn. This is Nova. Quarter turn right will give you this. This is Sail. Quarter turn, will give you this. Now, if you stack R cross BB on top of Nova BB, R cross BB is this on top of Nova BB. This is the fixed space that given to us for the picture. So if you want to stack one on top of the other, each of them will get only half of the screen space. So this is the Nova BB at the bottom, R cross BB on the top. Next example, you have Sail BB on top of R cross BB. Sail BB on top of R cross BB. R cross BB at the bottom, Sail BB on top. Again, each one takes half the space. Therefore, the picture looks squashed in the Y directions. Now, since you know how to do stack one on top of another, you can do multiple stacking. You can show stack Sail BB, which is this, on top of something else. So Sail BB taking half the space, and something else, stack R cross BB on top of Nova BB, they will occupy the other half of it. So each one will get a quarter. Alright, so R cross BB, Nova BB. These are the primitive. So what else can we do with just this? That is next, there's the combinations. So we can put things together to get lots of interesting pictures. Okay, let's put things together to see what we get. R cross BB. Now, let's take a quarter turn. We get this. Take another quarter turn. We get this. Similarly, Nova BB. Take a quarter turn. Another quarter turn. We have this. One more. Sail BB. Quarter turn. Another quarter turn. What do you notice? This is actually turning the picture upside down. Well, the tip at the bottom now. The bottom is now on the top, and it is reflected. In actual fact, what you see is this picture taking the upper edge, flip it down, you are seeing the back of this picture with a triangle on this side. But since you're seeing the back, to open it up, you need to flip it to see the front. You end up with the triangle on this side. So this is turn upside down. We can abstract this out to be a function as return quarter turn right of a particular picture. And we name this as turn upside down of a picture. The result of applying quarter turn twice to a picture is also a picture. And this function return a picture object. Now you see, turn upside down, it's just doing the right turn twice. And you can end up this. Let's do another quarter turn from this picture. You will get this. 3 turns to the right, it ended up with the picture same as a quarter turn left. So you do quarter turn right of the turn upside down, you get quarter turn left. Here is another look at it again. Seal BB and turn upside down seal BB is this. From here, if you do a quarter turn, you get this, which is the quarter turn left. And if you apply quarter turn left directly, you get this. So these two are the same. This is just an illustration of the previous slides. Now, we had this turn upside down, and we have this quarter turn left in section 2 as a form of abstraction. Now let's see more examples of abstraction that we can do. So we had before stack R cross on top of nova, R cross on top of nova, stack sales BB on top of R cross. So this is one on top of the other. Suppose we want to do one next to each other, neighbor. We want to have beside R cross BB, beside nova BB, or sale BB beside R cross BB, sale BB beside R cross BB. So let's see, how can we make this abstraction? Besides, so we define a beside function. Picture 1, picture 2. Picture 1 is this. This is our sale. Picture 2 is our R cross. So the result should be like this. So this was actually a turn right of a picture that R cross is on top of the sale. R cross is on top of the sales. If we turn right of this picture, we get this. This is the turn right that we have to do. Then how do we get this? This R cross is the turn left of picture number 2. Right? So picture number 2, we turn left, we will get this. And then picture number 1, this is actually also the turn left of picture number 1. So the turn left of picture number 1. Then the combination of this stack on top of each other. So stack R cross turn left on top of sale turn left, and then making a turn right, you will get this picture. With this beside, which is a new abstractions that we built from our primitive, we can then do more with this picture language. Here are a few nice pictures. They look familiar, but what are they? Well, they are from R cross BB, nova BB, sales BB respectively. If you know how to divide out the picture into 4 sub pictures for each of them. You see, this is R cross BB in some way, R cross BB in some way, same here and same here. Likewise for all this. What are they? This is actually the original R cross BB, and this is the turn left of the R cross BB, and this is the upside down of R cross BB, and this is the turn right of R cross BB. Likewise, you can do the same. Original, turn left, turn upside down, turn right. Same. Original, turn left, turn upside down, turn right. So you can write a function to make a cross. This is a cross. Divide the pictures into 4 sub-pictures. We use the beside to form the top, another beside to form the bottom. The original, it's here, the bottom left. The turn left, quarter turn left, is here, the bottom right. Turn upside down, R cross. Turn right, turn right. This is the left, the right, the left, the right. This is the upper left, upper right, bottom left, bottom right. So from this, we can make it an abstractions and change all the reference to R cross BB into picture and make it as make cross picture, return a picture. So with this, if you make cross R cross BB assigned to my picture, you show my picture, you will get this picture. So now you can have from here, you can get R cross BB looks like this. From the Nova, you make cross, you get this. From the seal, you make cross, you get this. Okay, let's get more. Show Nova BB, this is the picture given to you. Make cross Nova BB, we have this. What about if you make it one more time? You make cross with the make cross of Nova BB, which is this picture. You try to use this picture and make a cross. You get this. So forth. This picture is identical with respect to rotation of 90 degree. You take this, you rotate 90 degree, you get the same picture. You get identical 4 sub-pictures of this make cross Nova. What about 3 levels? Make cross, make cross, make cross 3 times. And what about 4 levels? Make cross, make cross, make cross, make cross 4 times. What do you get? Well, you get this picture. This 1 by 1 is you make cross 1 time. 2 by 2 is you make cross 2 times. 4 by 4 you make cross 3 times. 8 by 8 you make cross 4 times. It is tiring to write make cross many times. For example, if you need make cross 100 times, it will be very messy to write and count correctly. We should be able to do it with a number to the computer programs. This is the power of a program that allows some form of repeating. This is the looping, which is on top of what we encountered before on sequence and conditional statement for a program. Here is one realization of the looping with recursion. So you have repeat pattern function that's being called inside the function itself, within its body. We have repeat pattern calling repeat pattern with the number of times subtracted by 1. When it's n coming in, it will be n minus 1 repeated call. And the operator that we want to work on, it's called pattern. This could be the make cross or any other patterns that we want to make. So we call repeat pattern n minus 1 times that we wanted on this picture. The pattern is again applied on the result of this repeat pattern with n minus 1 times to make up to be n times. When this function is called with n equal to 0, that means there's no operation to act upon the picture. That is, we want to do this pattern on this picture 0 times. Then you just simply return the picture itself. This is also the so-called terminating conditions of a recursion function. So to repeat, you have a function that being called by itself within the body, but each time when it calls itself, it's reduced by 1 time. The result of this is being operated upon with the pattern that we want. When this recursion call enough number of times, each time minus 1, you get to n equal to 0, you will return whatever is the picture at that moment. So if you show repeat pattern for, make cross Nova, it is the shorthand of make cross 4 times. Now you can do the same for different picture. Let's take R cross. You have this R cross. If you make cross 4 times, you get this nice picture. This is R cross 1 time 1 by 1. 2 by 2 is the R cross 2 times. 4 by 4 is the R cross 3 times. And 8 by 8 is the R cross 4 times. What about you make cross 4 times on the seal picture? I leave it to you to try it out. Here is a quick note on how to write some shorthand. We usually define a function with the word def, define, square, for example, colon, return, blah blah blah. We can also write it as square, which is the name here, square, equal to lambda, x, which is the input, colon, and then the body. This one is the return value without explicit statement of a return, but it's the same. So this is the input, and it can be more than one, and this is the return without using the word return. So this forms, it's usually more formal, and this lambda notation comes in handy when we need to embed a function inside a function call, as we will see an example next. Let's see another example using the repeat pattern. In this case, we want to work on Nova. Show repeat pattern 3, n is 3 times. What do we do with 3 times? We want to apply 3 times of this function. Instead of the make cross previously, we now have this particular function, and it doesn't have a name. It is just simply lambda. Taking a picture returns a picture next to itself because of this beside. And this picture that we are working on is Nova. With this, applying 3 times, we get this picture. How do we explain this picture? This is applying this pattern 1 time. This is 2 times. And this is 3 times. Let's see another example. Here is another pattern which doesn't have a name. It just uses the lambda notation. Lambda picture, stacking a picture on top of itself. And this picture is again Nova. And we are doing this 3 times. And this is the answer. This is applying the pattern, stacking on top of each other 1 time, and taking this and stack on top of itself, you get this picture 2 times, and stacking it again, you get 3 times, and this is the picture. So far, what seems to be missing still? What we see so far are all pretty even, and at times, we want to see something odd and yet regular too. What I meant by this? For example, you have the R cross BB, looks like this. You can get this particular pattern 8 by 8 with repeat pattern 4 times, make cross R cross BB. You can get this with repeat pattern 3 times. And what about this? Let's say you want to have only 3 by 3. This is 8 by 8. This is 4 by 4. This is 3 by 3. 3 is an odd number, whereas all these are 8 by 8 an even number, 4 by 4 even number. Take another example. We have this R cross. We know we can put R cross on top of itself with stack R cross, comma R cross. We can also put R cross and 2 more R crosses here. This is by stacking on top of this R cross, which occupy half, and the other half is occupied by the 2 R crosses on top of each other. So you have 1/4, 1/4, half. What about this? 1/3, 1/3, 1/3. Is this possible? Well, all these are impossible with the given primitives we have seen so far. So we need to revise the primitives. We had clear all, show, quarter turn right, stack, working on all these images or pictures. We need stack fraction, using a fraction of the space for picture 1 and the remaining for picture 2. With this, we can then do what we saw just now. Let's see how we do it. So from R cross, we want to take 1/3, 1/3, 1/3, which means 1/3 and 2/3. To get this, we can do stack fraction 1/3 r cross. So we have this r cross taking up 1/3 of the space, which is here, and the remaining 2/3 of the space will be used by the next function, which will be stacking of r cross on top of r cross. So as a result, the 2/3 is equally divided between these two, and therefore each of it is again 1/3, and we thus ended up with this image. This is 3 parts. What if we need many more parts? Again, writing stack frac many times, it's going to be messy. We once again use recursion, as you will see here, to help us. Here is an example where we want to get the nova into 5 parts. Each of it is 1/5, and therefore the other 4 here it's 4/5. How do we do this? So we define stackn. N is the number of parts, n is a parameter, comma on a picture, colon. If n equal to 1, that means we just need 1 part, so we simply return the picture. Otherwise, return stack frac is to use 1/n of the space we have for the picture, leaving behind n-1/n space for the n-1 parts of the same picture. So to get this picture with this function, we simply say stackn 5, n equal to 5, working on the picture nova bb. Stackn allows us to make a column of the picture. We now go back to our problem of n by n of the same picture. Here's the example. We have the r cross bb here, and we make cross, we get this. Now we want to get 3 by 3 of the same pattern here. Previously, we only able to do it for even number, 2 by 2, 4 by 4, 8 by 8, and so on. Now we can do it with any number n, in this case 3. Here is an example. This is our r cross bb. This is the make cross of our r cross bb. This is the 3 by 3 of our cross that we want to make. We use the function n cross n. How do we do this? Well, there are many ways to look at this. You can see this as a column of the make cross, another column, another column. Therefore, you have 3 columns next to each other. The function that you could write is to make a stack of the crosses and find a ways to put them next to each other. Another way is you look at this as one picture here, another picture of the same on top of the picture, another on top of the picture. That means you look at this as 3 rows. So this is actually a column that rotated by 90 degrees to get this. So in this view, we can have define n cross n with n as the parameter and the picture that you want to make in the pattern. So you have stack n, comma pick. In this case is this make cross that we want to make 3 of them. And making 3 of them will be in one column. We need to rotate it quarter turn right to move it down to get 1 row like this. Then we can then stack the 3 of this same on top of each other to get this pattern. So return stack n 3, in this case the 3 of this picture on top of one another, and this complete the definition of n cross n. Let's apply this to nova bb. We have nova bb, show n cross n 3 nova bb. Oops, we got a little bit different from what we expected. The symbol is not in the right orientation. This is a slightly wrong version. We need a little bit of tweak to this to get it back to the same orientation as the original. We need a quarter turn left on the picture so that when we stack them and rotate it, they are in the correct orientation. So what is missing is this quarter turn left to counteract the quarter turn right here, so that the shape is of the correct orientation as in the original picture. So we have all these quilting patterns that we can see. Nova BB is like this. 3 by 3 looks like this. with the stack frac function added as a primitive to us. Here is the nova that we make cross first, which is this. Then you have a 3x3, 4x4, 5x5, 6x6, and 7x7. Now, as you can see in the past 30 minutes, once we have an abstraction defined as function, we can use it as if it was a primitive. And many of these are actually already defined in the runes.py. You do not have to key in yourself, but do note that the function n cross n is not in runes.py. To use n cross n, you need to key in yourself. To sum up, we have no idea how a picture is represented in doing all the above. We have no idea how the operation do their work, yet we can build complex pictures. Now it is your turn to be creative.